viewers, welcome to CEC lectures. Myself Dr. Preeti Tigwani from Department of Computer Science, Aribhat College, University of Delhi. So as you all are aware that presently we are learning the series of operating system concepts, and the module which we are going through currently is about CPU scheduling. And in the earlier lectures we have seen the importance of CPU scheduling, what are the terminologies within this particular module which we will be using in today's lecture. Those all kind of I can say a basic platform we have already kind of built in our previous lectures, and today we will be talking about the we can say what are the scheduling criterias, why do we need this scheduling, and then we will discuss about the scheduling algorithms. So with this background, let me start today's lecture, and the first kind of subtopic which I am going to talk about today is about the scheduling criteria. Now this is a very clear thing that in the multi-programming context there is kind of a context switch in which when a CPU is given to a particular job or to a particular process, this is going to the job or the process will either terminate or the control of the CPU will be taken in order to give the chance to other jobs. So definitely one job has to be taken the control of CPU, and another will be kind of given the control of CPU, and for this is the process of the CPU scheduling, and we need different CPU scheduling algorithms, but these different CPU scheduling algorithms should have different properties. That means if there are kind of, let's say, three ways A, B, C to choose which particular scheduling algorithm, these A, B, C are the scheduling algorithms which are choosing different jobs in which order these jobs should be given the control of CPU. So whether we will go with the strategy A, or whether we want to go with the B, or whether we want to go with the strategy C, that is what how are we going to decide that whether A is better or B or C is better. So basically what I am trying to say here is that choice of a particular algorithm may favor one class of processes over another, and basically we need to have some criteria which should be there for comparing various CPU scheduling algorithms. Now what is this criteria? There are kind of some parameters if we talk about these criteria. So the first parameter is CPU utilization. Now this whole game of CPU scheduling is about the keeping CPU as busy as possible so that we can utilize the CPU up to its maximum capacity. Now in an kind of a real standard system, what is the percentage in which CPU for which CPU is kept busy? So you will be wondering that if it is a lightly loaded system or a normal system, we can say only 40% CPU utilization is there. That means we will be using CPU up to 40% of its capacity in a case of a lightly loaded system, and if a system is heavily loaded having major jobs which are having high CPU burst, so in this situation this CPU utilization can go up to 90%. So there is a range from 40% to 90% tentatively, but the idea is we want to favor, or we want to adopt for the CPU scheduling algorithm which is going to keep the CPU as busy as possible. That means we want to maximize the CPU utilization. Another criteria under this is about the throughput. Now what is this throughput? Let us define this first. Throughput is actually number of processes that are completed per unit time. Within a unit time, how many processes you are going to complete, that is what you called is throughput. And for long processes, if there are kind of processes which are executing for long, this rate could be one process per hour, because the process is long and it is taking 1 hour to complete one process. And if the process is short, or if it is a short transaction, it could be 10 processes in every 2 seconds, or 10 processes per in every 10 seconds, or something of that sort. So throughput basically depends how kind of large your or how demanding your processes are in terms of CPU time or in terms of system time. So basically throughput is number of processes that are completed per unit time. Another criteria apart from CPU utilization and throughput is turnaround time. So turnaround time is basically the time when which is taken by a process to get executed. That means the interval from the time of submission of a process to the time of completion is known as turnaround time. So that is the duration in which we can say the process is submitted at a particular instance, let us say x, and the process is completed at a particular instance, let us say y. So y minus x, that interval or that duration is the turnaround time for a particular process, or simply we can say this is the sum of periods which is spent in kind of activities like waiting to get into the memory, because the process is submitted. Now it will it will be taken into the memory, then waiting into the ready queue, then executing on the CPU, doing input output, and all these context switch also. So the whole time when this was submitted and when the process is being completed, this whole time is actually known as turnaround time, and this turnaround time is the we can say sum of all the periods which are being spent by a particular process inside the system. For example, the period is spent waiting to get into memory, period for which it is executing on CPU, period for which it is doing some input output activity, or period for which it is waiting in the ready queue. All the periods when summed together gives you the turnaround time. So we have CPU utilization, we have throughput, we have turnaround time. Apart from this, we have also we also have one more metric, which is the waiting time. Waiting time is, we can say, the CPU scheduling algorithm does not affect the amount of time during which process executes or does input output. What is this being affected with is, it affects only the amount of time that a process spends waiting in the ready queue. So basically for how much time we are going to keep the process waiting, that is your we can say waiting time. It is the sum of period spent waiting in the ready queue and in the kind of other queues we can say. So here we have a ready queue, then we have an input output queue, then we have a device queue, and so on and so forth. So waiting time is for how much time your job is actually kept waiting, which is your actually we can say total time minus the time of execution minus the time of input activity, and so on and so forth. So only the waiting time is kind of summed up here. Another parameter here is the response time. So if we let's say in nowadays we have highly interactive systems. So in these highly interactive system, we can say the turnaround time may not be the best criterion in order to judge a particular system, because turnaround time is actually the kind of submission, actually the interval between your submission and the execution completion. So if it is a highly interactive system, that means it is kind of generating, the system is generating responses time to time. So that means the total turnaround time is not a good criteria in order to measure the performance of the system. So here we need to adopt another measure, which is response time, and thus this the another measure is the this response time is the submission is the time from the submission of the request until the first response is produced. Here I am not talking about the completion of the execution. What I am talking about is the first production of the first response. So the request is being submitted and the first response is being produced. This duration is actually known as the response time, and this is kind of, we can say, it is a well suited criteria if we are talking about some interactive system. So basically this response time, we can say, is the time it takes to start responding. It's not kind of when we can say the response is going to be completed or the execution is going to be completed. No, it is the time a job takes to start the responding, not the time it takes to output the response. So basically the turnaround time is actually kind of, we can say, is constrained by the speed of the output devices, while the response time has no kind of, we can say, connection with the speed of the output devices. So for an interactive system, it is better to take the response time as a criteria rather than the turnaround time. So here we have seen some criteria or some parameters which are the which are going to help us in choosing a particular algorithm over the another one. So these basically these we can say are CPU utilization, then we have seen throughput, then there is turnaround time, and then there is waiting time and the response time. These 5 criteria are there which are there to judge the performance of scheduling algorithms. Now with this background, if we can say, if we raise a question, why do we need scheduling? So basically we can run a program, we can run a single program at a particular point of time in a CPU, and if we need to run another program, we need to remove the previous one and need to submit the CPU, or need to take need to give the control of CPU to the another process or the another job. This process is going to this process is basically known as context switch, and that we have seen in our previous lecture. But the point is, how are we going to choose which programs need to run? So there we need some metrics to decide, like just for let's say for example, we have the amount of time until the it is going to end, or the time interval between which a function enters until the system enters the system until it is completed, and many others. We have also seen the CPU utilization, we have seen the throughput, we have seen response time, turnaround time, and so on and so forth. So all these are metrics to decide the amount of decide on various factors like the amount of time until the process is going to end, or the time interval between which a function enters the system until it is completed, and so on and so forth. So we need scheduling in order to choose one scheduling algorithm over the another, and these scheduling algorithm are based on various metrics which we have already seen. Now with whatever metrics we have seen, what are we trying to do? We have seen CPU utilization, we have seen throughput, we have seen waiting time, we have seen response time, and so on and so forth. So some of the criterias we want to, or some of the parameters we want to maximize, and some of these parameters we want to minimize. Now it is very clear that within these parameters we want to maximize CPU utilization and throughput. Throughput is nothing but the number of processes that are going to complete their execution per unit time. Also the utilization of CPU we want to maximize. These are the two parameters which we want on the maximum side, because we want the allocation of CPU should be fair. It should not kind of end up in having one particular job or having some particular jobs in the kind of, we can say, in the situation of starvation. Also we don't want any deadlock to be occurred. So allocation of CPU should be fair, and we want CPU utilization as well as the throughput to maximize. Now what are we left with? So if you can see on the screen, we are left with, in the criteria which we have already seen in detail, apart from CPU utilization and apart from throughput, we are left with a turnaround time, waiting time and minimum response time. And these are the three factors, or these are the three criterias which we actually want to minimize. So basically we want to minimize turnaround time, that is the time taken by a process to finish execution. We have already seen it in detail. Then we want to minimize the waiting time, that is the process as I have already told, that we don't want any process or any set of process to starve in either in ready queue or any other. And also we want the to minimize the response time, that is the time when a process produces the first response time. So we want to maximize CPU utilization, throughput, we want to minimize turnaround time, waiting time and response time, plus we want a CPU allocation policy should be fair, so that no job should get into the starvation. So basically based on these criteria, that these are the points which we want to maximize, these are the points which we want to minimize, and this is the general condition, which is the CPU allocation should be fair. On the basis of these, a process scheduler is going to schedule different processes to be assigned to CPU based on particular scheduling algorithm. Now what scheduling algorithm we are having? So we can have many scheduling algorithms, but there are 6 popular process scheduling algorithms, or 6 popular, we can say, CPU scheduling algorithms. These are, let us try to explore them one by one. Let's see the list first. So the first one is first come first serve, it is known as FCFS scheduling or FCFS policy. Then we have shortest job next, which is SJN scheduling. Apart from this, we have priority scheduling. Then we have shortest remaining time. We have round robin scheduling, which is also known as RR scheduling, and multi-level queue scheduling. So basically in all we can have 6 algorithm: first come first serve scheduling, shortest job next scheduling, priority scheduling, shortest remaining time, round robin scheduling and multi-level queue scheduling. So we will be kind of looking into all these CPU scheduling algorithm along with their pros and cons in one by one in detail. So let us start with first come first serve, which is FCFS scheduling algorithm, or we can simply say that the FCFS policy. So first come first serve, as the name indicates, jobs are executed on the first come first serve basis. So basically it's very easy to understand, and it is also very easy to implement this policy. So we have first a data structure which is queue, and queue is based on the FIFO strategy. FIFO is first in first out. So basically that is what that is equivalent to, or that is another way of saying first come first serve. So this for the implementation of the FCFS policy, we will be using FIFO data structure, which is nothing but queue. Also, this is a non-preemptive scheduling algorithm. So let me recall what is preemptive and what is non-preemptive scheduling algorithm. Let's say one particular job is it has taken the control of CPU and it is into middle of its execution, and the another jobs comes in, and because of any reason, the job which is going on, I am taking the control of job, control of CPU from that particular job. That means I am kind of, we can say, forcefully taking it. It has not completed its execution till now. So basically, and we are going to give that control to the another job. So this kind of scheduling is known as preemptive scheduling, and the another one in which we allow the job to terminate or complete the execution before taking the CPU control is what you call the non-preemptive scheduling. And we have already seen this preemptive scheduling and non-preemptive scheduling algorithms in detail in our previous lectures. So basically, we can see that my first come first serve is a non-preemptive scheduling algorithm, very easy to understand, very easy to implement. But the we can say when we talk about disadvantages, it is poor in performance. Why it is poor in performance? Because the average waiting time is higher in case of FCFS as compared to other scheduling algorithms. Now let us try to see an example which is given here on the screen. Here we have one table and one giant chart. So the figure which is given on the bottom side of the page under the table, that is known as the giant chart, in which what is this giant chart? Let me explain this first. So this is giving from which particular time or from which particular time instance starting, which is the we can say job which is going on. So here from 0 to 5 P0 is going on, then 5 to 8 P1 is going on. So basically we can say this is a kind of timeline on which we have represented the processes. Now as far as the information is given, we have a table which says that there are 4 processes named as P0, P1, P2 and P3. In the second column, their arrival time is given. So P0 is arriving at time 0, P1 is arriving at time 1, P2 is arriving at 2 and P3 is arriving at the third time instance. Then we have the execution time. So execution time is the time for which they need CPU. So we can say that the unit of the time here is, let's say, millisecond. So P0, the process P0 needs CPU for 5 milliseconds. Then there is process P1 which is looking for CPU for 3 milliseconds. P2 needs CPU for 8, and while P3 needs it for 6 seconds. And then we have their service time. So service time is, for example, according to the FCFS, which is the first come first serve policy, the P0 is coming first, which is at the arrival time 0. So we are going to give the CPU to this P0, and this P0 is going to keep the CPU for 5 seconds. So on the giant chart from 0 to 5, P0 is represented. So how much time P0 took in order to get serviced? It the P0 was not waiting at all because it arrived at time 0. The CPU was free and immediately it has been given control of CPU. So service time, or we can say waiting time, here is 0. While if we can see the row for P1, the arrival for P1 time is P1 is 1. So that means the CPU was busy with P0, because CPU was busy with P0 from 0 to 5. So obviously at instance 1 it was busy, and execution time it is looking for is 3, and this is coming second in the queue or coming second in the schedule, we can say, and it is looking for CPU for 3 milliseconds. So when P0 is going to finish its job at the instance 5, P1 will be given control from 5 to 8, that is for 3 seconds, which is its execution time. It is taking the control of CPU. So from 5 to 8 for 3 seconds P1 is there. Then in the kind of list, P2 with its arrival time after P1 is going to get the control from 8 to 16, that is for 8 we can say 8 milliseconds, because its execution time is 8 and also service time is 8, because it is starting from 8 milliseconds and it is going till 16 milliseconds. Now at 16th millisecond, at that particular instance, P3 is coming into the picture and taking the control of CPU for 6 seconds, that is from 16 to 22. So at 0th instance P0, after the completion of P0 there will be P1, because that is second in the queue, in the upcoming queue. Then came P2 and then came P3, and I have also said that this is a non-preemptive thing. So while P0 was getting executed till 5 milliseconds, all the jobs were, we can say, submitted, but being a non-preemptive thing, we are not going to take the control of CPU from P0 until it finishes. So, P0 finishes, then P1, then P2 followed by P3 and so on and so forth. So, waiting time here, which I have already explained, is about the service time minus the arrival time. So, for P0 it is 0 minus 0, and for P1 it is the different thing. So, if you can see the average waiting time, so average waiting time here is going to be high as compared to other we can say other algorithms, which we will be seeing shortly. But implementation can be easily managed with a first in first out queue. So, when a process enters the ready queue, some details about the implementation are: when a process enters the ready queue, its process control block, which is PCB, is linked onto the tail of the queue. So, basically we have we can say we have a queue of PCBs. So, whenever a process enter, its PCB is taken into the queue at the tail, obviously, because it is a first in first out structure, and that job is in now the queue and it is waiting for its turn. So, when the CPU is free, it is allocated the process at the head of the queue. So, one process is going on, it is terminated, completed its execution. Now, it could be out of queue. Now, we can see that what is available at the head of the queue, that process has been given the control of the CPU, and then the running process is that removed from the CPU from the ready queue. Running process is removed from the ready queue, we can say. So, one by one they enter in the queue, take the CPU and then go out from the queue. This is the simple policy, basically a non-preemptive algorithm, because once the CPU has been allocated to a process, that process is going to keep the CPU until it releases the CPU, either by terminating. So, the release of CPU could be either by the termination or by any input output request. Whatever way the CPU is going to be released, unless it is going to release the CPU, it is the CPU is not going to be allocated to any other process. If we can kind of see some characteristics and features of FCFS algorithm, this is particularly troublesome for some time sharing systems, where it is important to have where it is important to allocate each user a CPU at regular interval. Also, it would be disastrous to allow one process to keep the CPU for an extended period. So, for example, instead of let us say 16 milliseconds, a CPU is having let us say a CPU burst of a particular process is having a CPU burst of let us say 600 milliseconds. So, that is a quite extended period, and other kind of jobs will be kept on waiting, and because of this reason only the average waiting time is we can say is higher in case of FCFS algorithm. So, in this lecture we have seen what are the criterias on which the scheduling algorithm is based. Then apart from that criteria, those parameters, we have seen why scheduling algorithms are required. We have listed what all scheduling algorithms we will be going through in our upcoming lectures, and we have also seen one scheduling algorithm which is first come first serve in detail along with its pros and cons. So, simple to implement, but kind of with high average waiting time is the consequence of first come first serve. Here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed it. Thank you for a patient hearing.